So I'm Michael Jenkin. I was a student of John's a long time ago, about 30 years. It works out we started. And I'm going to talk a little bit about some of our experience with robots over the 30 years, many of which were done with John. And we started a long time ago. That was 1983. And we've been working a long time at these. And of course, we're still working on them. And of course, things have changed. We made spectacular advances as a field, and we have robots that do all sorts of amazing things. But attending to things in the environment is still a key problem, right? Attending to events, understanding the events, attending to people in the environment. And I'm not going to talk too much about the things that are there. That's actually work in the high bay at CSA using SLAM and then displaying the results in virtual reality so you can tell you operate the vehicle based on the model that you get back from that. But we've done a lot. And of course, this is not, all the work is done in large groups of people. There's lots of collaborators I work with now. I chose deliberately the picture where everybody wasn't looking at the camera, so you can't guess who's there. There's collaborators from long ago. You may be able to recognize some of yourselves there, youngish looking people. And I have a bunch of other collaborators who work in human perception generally and virtual reality, and they certainly collaborate with them too, but they're less related to this talk here. So when I started as a NSERC USRA a long time ago with John, we worked on that particular example, walking figures in stereo imagery. And as time went on, we started working on a project called the ARC project. And at the time, we basically solved everything there is to solve in autonomous robots working in nuclear power plants. And we solved them with, by the way, that's the commercial version up there. This video is available on the web if anybody wants to see a late 90s example of robots. But that's what a late 90s example of a robot looked like. And the robot attended to events in the environment, pre-mapped targets, and it had a pre-built map of the environment of where large obstacles were, and it augmented that with local information that it detected as it went along the way. That robot was fantastic. It weighs, we actually got rid of it very recently. It was sitting in the lab. It was brutally heavy, hundreds and hundreds of pounds. And just for those people trying to model things about robots, if you spun the robot in place, it would actually move along the nape of the carpet. So it would think it was in one spot, and it would slowly drift. And in terms of designing of vehicles at the time, that large thing at the front is an e-stop circuit. And when you hit the e-stop circuit, it only suspended the operation the vehicle was doing. So what that meant was that if it was crushing you against the wall and you pushed against it with your hand and then let go, it would then crush you against the wall. And the height of it was just perfectly designed to go under the center, between the seat and the wheels of a chair. So in fact, you could be sitting on a chair and it would slowly push you into a wall or a desk or things like that. But no students were ever seriously harmed in terms of that. And so that vehicle attended to the world. It attended to pre-mapped targets that were in the nuclear power environment. I don't know if there's one in the shot there. Probably not, because back in those days, color wasn't something you got in a camera. And then years went on, and this is Playbot and TRISH. So we had a still of TRISH a moment ago. And there's somebody who may recognize themselves there, back driving the motors on the robot. And TRISH attended to the world using this spectacular stereo head, which, by the way, has torsional eye movements. The eyes can do this too, as well as moving in pan and tilt, as is being explained there, I'm sure, to the video sequence at the time. You have no recollection of that, do you? And now this is, by the way, the state-of-the-art computer animation of the same thing is shown over here. And I seem to remember this was like rendered a frame at a time on like a SGI Indigo desk side thing, and hundreds of hours, and they're written out one frame at a time. So the robot that this thing sat on was a LabMate. Do you remember LabMates from days of old? Differential drive vehicle. Anyway, that will come back later on in the talk. And so we built a lot of different devices. TRISH moved on. That's a color version, I think, of this black and white from the paper. TRISH turned into that, which I think is still running in Rick's lab, or it was last time I looked. So you can build hardware a long time ago, and it can still be used. And this idea of attending to things in the environment, something that John has certainly driven home for years and years and years, of course, goes on in other spaces. You can look at attending to where you'd like to put the various cameras in a robotic head to look at something. So that was a virtual trinocular head we built in around 2000. And in looking at attending to things that are both real and imagined. So for example, we did some work with the Canadian Space Agency a long time ago too, 2001, looking at trying to recover reflections in various reflective surfaces on the International Space Station. And that's an example of doing it with a trinocular stereo head from about that time. So that was a long time ago. And of course, technology's improved. First of all, we have color pictures rather than black and white. But the robots themselves have improved. And so again, though, this task of attending to what you would like your robot to look at in the environment is a really critical sort of problem. And so along the way with Greg, we started looking at doing things underwater. So when Greg and I were grad students with John, there was a PI group that used to meet, I'm sure quite illegally, off campus at a particular spot in somebody's backyard. And we always bemoaned the fact that graduate students in computer science got to spend the entire summer in the basement somewhere playing with computers. What we really wanted to do was to go somewhere much more exotic. And so years went by, and we decided what we'd do is look at underwater robotics, because that would give us an opportunity to do that kind of thing. And so around 2006, we built this thing. You just saw a little video of it playing there. And it's basically an IMU stereo sensor. It has the state-of-the-art stereo device on there, as much hard drive space as we could stick into the box, and an IMU. And the IMU is a huge thing. It's a big block in the middle. And it was actually, we got it from a company that makes them for torpedoes, which was getting out of the business around then. And the idea, of course, is you could build 3D models from every frame, as is shown up there, compute ego motion estimation from the IMU and the stereo field, and use that to build three-dimensional models. And before I show that, of course, the technology advanced somewhat. That little blob that fitted in that thing is now this little thing that this person is carrying here. And that's actually me. So by the way, if you stay in computer science long enough, you'll find an excuse to do almost anything. But the whole technology is now a little box inside that. And most of what you're seeing there is actually a light and a battery pack to make the whole thing work. And so you can swim around. Now you'll notice that the nice thing about this is that the question about where to look next is all being decided nicely by the diver who's swimming around. And of course, I'm using a very high level understanding of what the world looks like in order to make that work. But given that you have a sensor like this going over space, you can use that to build a nice three-dimensional model of what you have. This is what, a decade ago now, I guess. And so, you know, there's the left and right views. The upper left frame is the local ego motion estimation. It's done over 3D point clouds. So you can feed the optimization process from the IMU data. You can use that to, in a robust statistical framework, to figure out what the ego motion of the device is. You can take your point cloud and then you can move that over time, and you can also estimate the motion of the robot. That's what's being shown in the upper right-hand corner as the user interface pulls back from what you see. And by the way, it turns out that the big problem then becomes rendering this thing, because it's a ginormous point cloud, and you have to be able to do something with it when you're done. So what you have is a system that lets you build models of in-situ things underwater or in other places. And the similar kind of technology has, of course, been used by lots and lots of other people since then. And we did some work with MDA about, I don't know, 5 or 6 years after this, with a similar kind of technology that they developed called Instant Scene Modeler to build models of things like crime scenes and other sorts of stuff. Anyway, it's really quite interesting because you really do see the voids that get generated because you're not looking where you should look. And so this problem of understanding where you want to look and where you want the sensor to look is a really important task that really hasn't got a good solution to it yet. So one of the complaints that people have about the work is that we always do this stuff in really delightful locations like Barbados. And so just to show you that we don't just do that, this is doing it in Lake Ontario. So this is a wreck. It lies just off of Humber Bay. So if you were to take the ferry over to to the island airport, and you looked west as you did it. There's a buoy about a kilometer away, and at the bottom of the buoy is this thing. It's a very famous shipwreck. It was a British man of war that was captured by the Americans in the American War of Succession, which you may know as the American War of Independence. And it was then eventually converted into a barge and sank in a storm. And this is running the algorithm there. And this was some work we were doing with the point gray cameras, and we discovered the point gray cameras have very poor low light performance. So this particular set of images caused us to change the sensor in a dramatic way. But visibility and computing ego motion estimation in Ontario is quite difficult. This is imagery collected from a lake just north of here in King City, and that's what visibility looks like here. Right? And one of the problems when you drive your robot in a space like that is if you touch the bottom, that's what you get. And so one of the things that we're looking at is taking the technology that works in beautiful places like the Caribbean and getting it to work in environments like that, and we've had some success. So once you've got a sensor system like that, you'd like to build it, embed it in some kind of robotic platform, and I'll leave Greg to chat about this little guy here on the left. This is the Aqua 2 platform, which you may have seen. It's for sale from a company called Independent Robotics, and we have business cards we'll hand out later if you'd like. The one on the right is a more traditional thruster-based design that's called Milton, named after the brave little toaster from the movie the same. And both of these things are really interesting devices. They have to exist in a 6DoF environment. They have to exist in an environment where the sort of standard visual frames that you get when you're running a robot inside don't exist. There are very few flat surfaces, for example. There's currents and wave and other effects. And one of the really interesting things in terms of building robotic systems that run in these kinds of environments is that the environment is not very forgiving of failure. Water getting into these devices in salt water leads to all sorts of unusual and complex things which usually cost a lot of money to fix. And many graduate students have realized that if you don't attend to the little details like making sure the device is closed, your master's thesis or PhD thesis may be delayed slightly while we fix the results of your mistake. The other thing to note is that these things are running in the open ocean, and if your robot suddenly decides to take off at a speed faster than you can swim, you have to go and, again, your thesis may be delayed. And we have lost the odd device. I refrained from putting the video of that in there. So we built a lot of robots, and we built different kinds of robots. They don't all work underwater. Some of them work terrestrially, and I just thought I'd show one of these. So this is a project we did with an artist. And this project was called The Sailing Stone, and his idea was to build a piece of sculpture that would slowly interfere in the motion of people through the art gallery. So the idea is that, so that, of course, is a lab mate inside there, which is why I included this thing. And that's a lab mate which has been, things have been added to, like we changed the batteries in the controller and added more power and all that kind of stuff. But it's basically a big hunk of granite with a lab mate stuck underneath it. And what happens is a network of cameras, it figures out the motion of people in the environment, and then the robot slowly moves the piece of statuary so that it blocks the most commonly followed pathway in the environment. And so his idea was he wanted a piece, rather than having statues that don't interact with people, this one interacts with people very, very slowly. And it moves very slowly, like it moves like a centimeter a minute. And so you really don't notice it except when you look back to see this piece of statue that's moved, which is kind of a cool thing. And we ran this in Very Hall for a while, which was kind of neat. And of course, there was a network of cameras and the usual kind of bits of technical stuff to make the whole thing work. So that's the way the way the world has been working. But there's lots of interesting things that still happen. And I thought I would include a couple of slides about some of the things that are ongoing, and because these relate to some interesting attentive projects that still run. This is the Dragonball. So spherical robots are interesting, right? I mean, they're interesting for lots of reasons. You can seal them from the environment. Recent Star Wars movies have them with balls stuck on the top and the like. But they introduced a whole bunch of really interesting problems in terms of actually making the robot do something interesting. So any sensor you happen to put on the robot, of course, is going to spin as the robot moves, unless you have like a little hat on the top or something. And so you have this really interesting multi-queue integration problem where even if you wanted to have sort of a standard teleoperational camera view sticking out of the robot, what you want is that camera view to be stabilized by gravity. And so here's the robot spinning along, and the little white things you see going around are actually these little blue cable ties that are holding the edges together. So in fact, the robot is, rolling down the world, but as an operator's view, you get to see just the world as it is. And so what's interesting here is, if you were a user and you wanted to actually attend to this thing moving, what you really want is not to attend to the actual motion of the vehicle, because you really don't want to be confused by the vehicle spinning. Your camera view would see the ground, the ceiling, and so on. What you really want to see instead is the world as though you were just hovering above the surface. And to make this work, there's two wide field of view cameras mounted on the axle. And so this view is actually being synthesized from the output of those things, corrected from information from the IMU as the robot runs along. And so there's interesting problems there about how to get the data from the IMU, which will be correct, but at a slightly different time base than the data from the two cameras, so that you get a more or less stable view as the robot moves. And that's so just to give you an idea of the world, how small the world is. So this is work that Bikram, who's working at York, who used to work for Greg, and Greg and I used to work for John, how tight the whole world happens to be. And Bikram, when he finishes, hopes to work for John. So, that's incestuous would be another word for how that all works, I think. Another issue in terms of working with robots underwater is actually communicating with them. So it turns out that underwater, a substantive problem is that it's actually quite difficult to talk to the robot. So a lot of the work that had been done by our groups for many years involved cabling the robot to the surface. And so what that meant was that you had somebody on the surface who, and maybe that the cable then went all the way back to the shore, because that's where power was and data was and warmth and safety and all that kind of stuff. So someone on the shore would say, the robot's not working, and yell to the person out in the water, who would then try to communicate to the person underwater by splashing or whatever. And then they would do something and bring the robot up, and hilarity would ensue. And so various mechanisms have been proposed by various people to try to solve this, using pre-printed targets or having electronic control devices underwater to make the whole thing work. But clearly the thing you'd really like to do is communicate with the robot via gesture. And that's actually how people talk underwater. There's a well-developed language for how you talk to somebody else underwater. Getting somebody's attention is actually quite difficult, because sound is sort of omnidirectional. So like, even if you bang against the side of a tank or two bits of metal together, it's extremely difficult to know where the sound is coming from. But once you understand where the sound is coming from, you can look at the person and try to interact with them. So one of the things that we've been doing recently is building a standard neural net that doesn't understand anything about how the whole thing works inside, to build a system that can recognize standard hand gestures underwater. And these are the PADI hand gestures, the recreational diving hand gestures. There's another set of hand gestures that are known by commercial divers, and I'll get to that in a second. And so given that large data set that we've been collected including in the Caribbean, we've built a system that does exactly that kind of thing. It does standard hand gesture recognition, but it does it in the underwater venue. The other thing here is that's Milton, and you saw a shot of it, but the standard way we talk to the robot now is via some kind of cabled box. That actually has a piece of Android hardware in it, and there's an Ethernet cable that connects the two things together, so you can drive the robot from a distance underwater, and so you can be in close proximity to the vehicle when you're doing something of interest. It turns out that although this is a fun place to do the work, most of the industrial applications for this task involve spaces like the shot that's up there on the right. And that's deploying Milton in a lake nearby. And this is what it's like trying to collect hand gesture recognition in a real-world environment. Right? So that person is so they're reading the task, right? What's the next thing what's the next hand gesture I want to do? Right? And you have to guess, based on that, what the gesture is. Any divers here know what that is? That's low on air, right? And you have to be able to see that, and divers can see it and respond to it. Although, why you say that to a robot, I'm not sure, but we use the same gesture sequence. And that's the kind of task environment that we're looking at doing the task in, right? Is getting it to run in this kind of environment. By the way, that person is about from here to that table away, right? There's out of air, right? And that's how you dress if you're a commercial diver. So in my... I don't see a regulator going to... No, it's a big sign that says we're all practicing these things, right? This is not quite as clean as the cave environment you showed the other day, right? By the way, it gets much worse than that. We were doing some work during the ice storm about 3 weeks ago, if you can believe there was an ice storm here about 3 weeks ago. And the visibility was about 8 or 10 inches, so none of this would have worked there. And then, finally, watching my time here, there's this task of attending to people and interacting with them. So this is a project, wrapping the whole thing back up, this is a project that involves John and myself and a number of partners here today. And the question is, can we put a face on a standard, a social interaction robot? And so if you take a sort of a standard robot, it looks like this. It's got a computer display there. There's not a lot of local computational power. And what we'd like to do is put a realistic face on the robot. And so, well, one obvious thing to do is to take the rendering that we'd like to have done here. So maybe to back up for a second, the robot uses the cloud. You speak something. Whatever you speak is sent to the cloud. Take your favorite cloud-based recognition system, Alexa or somebody else's. It does the recognition. It sends it to your favorite AI engine in the cloud. It does the answer. It takes the answer. It sends it to your favorite AI engine in the cloud, and that produces a vocal utterance. It sends the vocal utterance back, and it speaks. What you'd like to do is to add a face to that. And so, of course, there's not enough computational power in this thing to render any kind of realistic face there. And so what you'd like to do is to take advantage of the fact that the cloud can do the rendering. And so we do exactly that. We take the information, we do the rendering in the cloud, we take the parts back from the cloud, and we put it back to the robot. And when you get back from the robot is now a face that talks to you. And I'll come back to that in one more second. And so I guess sort of in all of this, a key aspect is that you have to have your robot attend to people. It has to understand and to the environment. It has to understand what the environment looks like. It has to understand what people are trying to do to it. And based on that, it has to come up with some kind of intelligent response. And that was true a long time ago with these robots. You may recognize one or two of those in the world. It's true now with various robots that are running now. This is a similar robot that's to the earlier talk that does path planning on paths at York. And it's true with robots like this. So this is, how new something could be. This was yesterday, I think.
Congratulations, John.
Congratulations, John.
Congratulations, John.
And so we can put any kind of avatar we want on a particular robot, and we certainly have. Anyway, congratulations, John.